Okay, so for the first one here, we're going to use the formula for the period of a pendulum, right? So T is 2 pi square root of L over G, right? And that's the length of the pendulum. And this is what, that's just 9.81, right? So presumably pendulums will swing slower on the moon, etc. Okay. Now, all we have to do is figure out what the period is, and we can figure out the length of this thing, because presumably we're on Earth. Okay. But they're doing something sort of tricky here, right? You're tempted to say, oh, well, the period is 1.125 or something like that, right? But just be careful because this is the kinetic energy, not the velocity. Okay, so let's imagine that the velocity does this. Okay, so suppose we've got like that, right? Remember that the kinetic energy, if we do the same graph as kinetic energy, you're going to have a maximum here. Remember, it's v squared. Kinetic energy is 1 half mv squared, right? So it's like the absolute value of this thing, right? Well, so it's going to have a maximum here and a maximum here, right? So it's going to go up, nothing, up. It's going to have a maximum here, nothing, up. You know, if I could draw a good sine wave, but notice that this thing, that a full cycle, we really haven't gone through a full cycle unless we've gone from like here to here. So right? So it's really, it looks like two full cycles of the kinetic energy, right? So our period is, we have to read from here to here, because if we draw the velocity, if I graph the velocity, let's imagine that's zero velocity, right? This could say be positive, right? Then it goes through zero here, and then it gets fully negative, right? Then it goes through zero here and positive, right? So that is one full cycle. It'll start off with a positive kinetic energy, and then when the velocity is negative, the kinetic energy will be positive, right? And then when it goes through with the origin, right, the kinetic energy will be zero, and then it becomes positive. So our period is 2.25. Okay, plug that in there, plug 9.81 in there, solve for the length. And the length is between 1 and 1.5 meters. Okay, I'll tell you that much. All right, so label on the graph the letter x at a point where the speed of the pendulum is half its initial speed. Whew, that's crazy, right? Well, what does that mean? If it's half the original speed, then it's 1 half, if 1 half mv squared, right, is our kinetic energy, right? At 1 half m, 1 half that velocity squared, right? Well, that's just going to end up being 1/4, 1 half mv naught squared, right? The 1 half squared becomes 1/4. If you cut it in half, you divide the energy by 1/4, right? So what is 1/4 of 20? You can just mark, and basically you can just mark any place where the kinetic energy is 1/4 of 20, okay? Okay, let's see. The mass of the pendulum bob is 75 grams. Show that the maximum speed of the bob is 0.7, right? So our kinetic energy is 20 millijoules, right? So 20 times 10 to the minus third joules, right? Or 0.020 joules. Okay. And let's see, the mass is 75 grams, so 0.075 kilograms, right? And then just use this formula, 1 half mv squared is the kinetic energy, right? Plug that in for your kinetic energy, plug that in for your mass, solve for your velocity. And I got something between 0.7 and 0.75 meters per second. So it's not exactly that. Make sure you show, whenever they say it's about that, make sure on all those problems that you always show the next sig fig, okay? Because they're looking for it. Because that answer is given, right? All right, let's see what else there is. Oh, then they throw in some momentum, okay? So there's this, when the 75 gram bob, don't you feel like they should capitalize the bob, right? That's its name, right? 75 gram bob is moving horizontally at 0.8 meters per second, which, by the way, it never does in the graph before, right? That velocity is not 0.8, I'm just going to say. It collides with a small stationary object, also of mass 0.75 grams, right? So I'm assuming this is something like beeswax, and these guys just stick together, right? Calculate the speed. So use conservation of energy, of momentum. Sorry. Okay, so mv is going to turn into m plus m times v, right? It's pretty simple. I mean, if you double the mass, what's going to happen to the velocity? Okay. Okay. Show that the collision is inelastic, right? Remember, inelastic means you need to state that inelastic means the kinetic energy is not conserved. You need to show the kinetic energy before. So the energy before is going to be 1/2 one of the masses, right, times this velocity squared, right? Afterwards, it's going to be 1/2 the combined masses, right, times whatever this velocity is. I'll call it v prime squared, okay? That's v prime, whatever that velocity is afterwards, right? Okay, now I get it going down by a factor of 2. It decreases by 2. In the mark scheme, they said you have to talk about inelastic, and then you also have to show the difference, which I don't know, didn't make sense to me. Like it loses so much energy. Okay. All right. Then it says sketch on the graph to show the variation of gravitational potential energy with time for the bob and the object after the collision. The data from the graph used in A is shown as a dashed line for reference. Okay, so this is the velocity, right, or the kinetic energy. Sorry, the kinetic energy. Presumably, this is 0.20. Okay. Now the new energy is I got like 0.12 as the final energy, right? Okay, so we're going to be peaking out at about 0.12. So when there's no kinetic energy, we're going to have a maximum potential energy. When there's maximum kinetic energy, we'll have no potential energy. Again, when there's a maximum kinetic energy, there will be no potential energy. When there's no potential energy, there will be a maximum. And I'm getting this for me was 0.12. Okay, now that's interesting. When you get to the mark scheme, you'll have to let me know what you think. Okay, so you want to draw yourself a nice curve that goes a sine curve, kind of a what is it? I guess it's going to be a I guess it's going to be like a sine wave, just a sine wave like that. Okay, draw that through there, and yeah, all right. I think that's it for this guy.